Welcome to the second video of organic chemistry tutorials. For this part, we're going to go over functional groups. And so the first functional group, or I should say first three functional groups that we already went over are alkanes, alkenes, and alkynes. So alkanes are single bonded carbons, alkenes are double bonded carbons, and alkynes are triple bonded carbons. And then alcohol is a OH group, and I'll put a dash next to it indicating that it's a substituent off of any R carbon chain. And amines are any nitrogen attached to either hydrogens or carbons. Alkyl halide is any R group with a halogen, so it could be fluorine, chlorine, iodine, or bromine, iodine. And nitro groups is just a carbon triple bonded to a nitrogen. Some other groups, a large group of functional groups are called carbonyl groups, and it's just a carbon double bonded to an O, and the substituent, one of their substituents from the double bonded carbon dictates what type of carbonyl it is. So for aldehydes, it is a hydrogen. For ketones, is both an R group on either side. Carboxylic acid has an OH group on one of the side of the double bonded carbon, and then esters have an OR group. Now, one thing to note is that there's another functional group that sounds a lot like esters. It's called ethers. And what an ether is a oxygen in between two R groups, in between two carbons. And so one thing that really helps memorize or separate these two functional groups, not get confused, is to just compare between the carboxylic acid and ester instead of thinking about ethers, and also writing out the name or writing out the structure when given the name, and then vice versa really helps to memorize all the functional groups. Okay, so now that we've gone over all the functional groups, let's go over degrees of substitution for functional groups, and especially there are two functional groups that we need to talk about regarding degrees of substitution. Those are alcohols versus amines. Oh, before we go over that, I also forgot one last functional group, which is in the carbonyl group, and they're called amides. And this functional group actually has it also sounds very similar to amines, and that's why it has a nitrogen attached to any two groups. So it could be R group, but I'll just have lines to it, but it could be hydrogens or carbons. And so back to what we were talking about, alcohols versus amines. So alcohol degree of substitution depends on the carbon connected to the alcohol. What I mean by that is there's a carbon chain. We would look at, instead of the alcohol, we will look at the carbon that it's attached to and determine its degree of substitution, and that directly correlates with the substitution the type of alcohol it is. So since it's 2 degrees substituted, we will call this alcohol a secondary alcohol. And for amines, it's the opposite, where you would, instead of looking at the carbon directly attached to the nitrogen, we would look at how many carbons the nitrogen is attached to. So if there is 1 carbon attached to it, this would be a primary amine. And I recommend practicing this either from the end of textbook questions and just get used to the functional groups, as well as naming amines, types of amines, and types of alcohols. One thing I need to mention that I forgot in the previous video is alkenes, alkynes, hybridization, bond angles. And so for an sp3 hybridized carbon, since this is a 3-dimension, a tetrahedral, where it would come off like this, basically, like that, we observe that there is 109.5 degrees bond angle for sp3. sp2 has, from a carbon chain, if we look at an alkene double bond, we can see there is a 120 degrees bond angle. And for sp hybridized carbons, we can see that there is 180 degrees bond angle. So this is why when we're drawing alkynes, we want to draw a straight line when we're drawing alkynes, and then we can do the zigzag trans bond line. So keep that in mind when you're drawing structures. So moving on, let's talk about IR spectrum. So the IR spectrum, or spectroscopy, it's just a way where using infrared light, we can see what type of functional groups exist in a molecule, depending on how much absorption there is, or reflection, I guess, of the IR light. We can see like which specific types of functional groups exist in a molecule. And so if we were to be given a graph and to identify each functional group in this from this graph, we would typically be given also a formula. So C N H N and stuff like that. And so one of the 3 important functional groups that really is easy to spot in an IR spectroscopy graph is the alkynes. And so for alkynes, there's two types of alkynes. Internal, so I'll do this in a different color, internal and terminal. So what I mean by that is internal is an alkyne, a triple bond existing within a carbon chain, while terminal is at the end. And so the key differences is that for alkynes, internal alkynes, there is a range of 33,000 centimeter to the negative power, and also a frequency at 2200 that are and the peaks are pretty sharp. And while on the other hand, terminal alkynes would only have 3300 frequency. And so when we look at the graph, for example, compared to each other, the internal alkyne should at least have around 3300 and 2200 two peaks, while the terminal alkyne should have only one sharp peak at 3300. And so this is one of the functional groups that's really important. Another one is alcohols. So alcohols. And the alcohols are really easy to spot because from the IR spectrum there is a U, a large dip that exists towards the higher frequency range. And so the frequency range would be around 3600 to around 3500. So if you just see like a big U, that indicates it's an alcohol. And finally, carbonyl groups also can help identify what type of molecule you have and what functional groups exist within this molecule. And so carbonyls have a 1600 to around 1700 range. So I'll just put it in here. And an example would be around the 1600. There should be like a sharp peak. Interestingly enough, for carboxylic groups, or just amines or carbonyl groups in general, they kind of separate the frequencies. So, for example, a carboxylic group right here, we would be able to see this carbonyl 1600 to 1700 frequency range, and also the big dip around 3600. So keep that in mind when you're looking at carbonyls. Also, in addition to just knowing certain frequencies and what they look like on the IR spectroscopy graph, IHD would also help identify if there are any pi bonds. So IHD is just stands for index of hydrogen deficiency. So basically, in any straight chain alkane, we would observe if we know the number of carbons. So for this one, it would be 5 carbons. Typically, the number of hydrogens is equal to double the carbons plus 2 for an alkane. So if we do that, we would get 12 hydrogens. And we can prove it as well by just simply marking each number of hydrogens, since we know carbon wants 4 bonds each, and we can count them. So there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 hydrogens in a 5-carbon chain. Now what happens is for alkenes, or any number of pi bonds as well as rings, ring structures, they decrease the hydrogen count. And so when we look at this, there is actually so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are actually 5 carbons and 10 hydrogen. And so by using the IHD formula, which I'll show you the longer version, and then I'll show the shorter version, which is 2C plus 2 plus nitrogen minus hydrogen minus any halogens over 2. Now this is the longer version formula, but also what you can do is just shorten it, because we know that carbon or the number of hydrogens is 2C plus 2. We can just do 2C plus 2, which is the normal number of hydrogens, minus actual number of hydrogens given to us from the formula, and we just divide it by 2. And so this is the shorter or condensed formula. Now, on the other hand, what if a problem were to ask what is the index of hydrogen deficiency when given a molecule? We would just be counting the number of pi bonds plus the number of any ring structures. And so for this one, let's say we have a benzene group coming off as well, so we would just call it a phenyl. And so what we would do is just count 1, 2, this entire, or I should make this smaller, this entire ring, that would be 2, and then each individual pi bonds within this phenyl group would be counted each as 1. So there is a total of 1, 2, 3, 4, 5 things that we need to count. So the IHD of this molecule is equal to 5. It's as simple as that. So IHD is just, when you're asked to give the IHD from a molecule, it's just counting the number of rings and number of pi bonds. On the other hand, if we were given the formula and it says that there is, let's say, an IHD equal to 2, this gives us the possibilities of either 2 pi bonds, 2 rings, or 2 or one pi bond and 1 ring. So for pi bonds, it could be either 2 alkenes, so 2 double bonds, so a structure that has 2 double bonds, or it could be, a triple bond, right? And the other options are just self-explanatory, but yeah. So keep that in mind. And so using IHD is really useful when you're given a formula to figure out whether there is any possibilities of alkenes, or most notably alkynes, because we know what it would look like.